Hello everyone, here is the representation for the paper Weakly Supervised Monocular 3D Object Detection using Multi-View Projection and Direction Consistency. Here is our motivation. Monocular 3D object detection has become a mainstream approach in autonomous driving due to its easy application. A prominent advantage is that it does not require LiDAR point clouds during inference. However, most current methods still rely on 3D point cloud data to label the ground truths used in the training phase. This inconsistency between the training and inference makes it hard to utilize large-scale feedback data and increases data collection expenses. To bridge this gap, we propose a new weakly supervised monocular 3D object detection method, which can train the model with only 2D labels marked on images. This is our contributions. In this work, we propose a novel weakly supervised method for monocular 3D object detection. Our method only utilizes 2D labels as ground truth without depending on 3D point clouds for labeling, making us the first to do so. We incorporate projection consistency and multi-view consistency to design two consistency losses that guide the prediction of accurate 3D bounding boxes. Additionally, we introduce a new labeling method called 2D direction label, which replaces the 3D rotation label in point clouds data. We also introduce a direction consistency loss based on the new labels. Now, let me introduce the details of the proposed method. This figure shows an overview of the proposed architecture, in which the proposed method is general and can be incorporated with most previous monocular 3D detection methods. To avoid the need for 3D point cloud annotations during the labeling procedure, our work only employs 2D ground truths of images. An intuitive idea is to project the predicted 3D boxes into the 2D image space, and ensure that the projected 2D boxes are consistent with the labeled 2D boxes. We define this property as projection consistency. By using the intrinsic matrix of a camera, you can convert a point in real-world 3D space into a point in 2D image space. This is achieved by performing a matrix multiplication with the intrinsic matrix. Thus, the 3D boxes with 8 corner points can be transformed into their corresponding points in 2D space. Subsequently, a 2D bounding box can be generated by calculating the minimum and maximum values of the x and y coordinates, as shown in the figure. Finally, loss values are computed between B and the 2D ground truth. The projection consistency constraint constrains the predicted 3D boxes to be within their corresponding projection regions. As shown in Figure A, all 3D boxes have the same 2D projection box. This means that there may be more than one optimal model solution with only the projection loss. However, to find the exact position of the target, we need to find additional constraints to achieve our goal. If an object is observed from two different viewpoints at the same time, it will show different projection views in the two images. However, its 3D bounding box in the real world remains the same. This means there is an inner consistency between the observations from different viewpoints, which we call multi-view consistency. As shown in Figure B, two different viewpoints have two independent projection regions, each with a set of optimal solutions constrained by the projection loss. However, when the rotation angle of objects is fixed, there is only one common solution for the two sets, which is the target box. In addition to position, all the 3D attributes of one target would be the same when observed from a different point of view, such as size and direction. The last consistency presented in this paper is the direction consistency for guiding the prediction of the direction scale. In previous works, the 3D rotation direction is labeled on point clouds by a vector from the center to the front of objects. To avoid the need for 3D LiDAR data, we propose a new labeling method named 2D direction label directly on pure camera images, indicating the 2D direction of the object in the images. The predicted 3D box rotation should be consistent with the direction in 2D space when they are projected, i.e., the direction consistency. Based on this consistency, we further design a 2D rotation loss for optimizing the rotation scale estimation. Experiments show that our trained models can achieve comparable performance to some fully supervised methods. We believe that the proposed method can utilize the rich data from production cars, which contain a larger variety of scenes than experimentally collected data. This is critical to improving the robustness and generality of models.